Good afternoon. My name is Yechang Kim, and I'm preparing together with Hyewon Kim. Today we will presenting our final project on boost converter and PPT for the power electronics course. So let's get started. Just a second. Yes, our presentation is organized into four sections. First, we will analyze the environmental data and we introduce our chosen MPPT algorithm. And second, we will take through the hardware and software design of the boot computer control system. And third, we will present design verification and simulation results. And finally, we will close with the discussion and conclusion. So looking at the solar irradiation data collected from January 29th to February 5th, um, we observed the significant variability across all measurement days. In particular, on January 30th and February 5th, rapid irradiance fluctuation suggested in intermittent could cover, which can be interpreted as a partial shading conditions. So this variety means that the maximum power point changes continuously throughout the day, requiring an algorithm capable of dynamic real-time tracking. So based on this analysis, we selected the below antenna search algorithm, or BAS, as our MPPT method. So unlike the conventional perturb or observe like BAS, BAS simultaneously sample power from both sides of the current operating point, making it well suited for environments where the MPP shift rapidly. It also has a simple implementation with low computational overhead. So moving to the hardware design, the panel we use is Kyocera K3 like this, with STC rated parameters of VMP of equals 23.6 volt, and IMP was 7.42 ampere, and power max was 75 watts. The short circuit current was like this, and open circuit current you can see through the PPT. And one important structure change from the standard boost converter is that the placement of the input capacitor. But because in conventional boost converter, the capacitor is placed at the output. But however, for MPPT application, we moved it to input side between the PV panel and the inductor to stabilize the PV voltage and enable accurate voltage sensing for the control loop. And for hardware design, yeah, I'll put here maybe, yeah. We designed the passive component under STC condition, since STC represents the most severe operating environment in terms of both radiance and temperature compared to our measured data average of 419 and at 44.51 degrees Celsius. So battery voltage was set to 30 volts, and this ensures the converter always operates in step-up mode, since VB must exceed VOC, which is 29.2 volt. So the inductor was selected for a 30% current ripple with VMP and duty cycle of 0.21. So we calculated inductor was 22.2 millihenry with the series resistance was 0.03 ohm. And the capacitor was designed for a 0.5% output voltage ripple, and the calculated value was 5.9 millifarad, and we selected 22 millifarad from within the given specification, a range of 22 to 100 millifarad. So, yeah. So, for software design, we first need to linearize the PV panels nonlinear IV characteristics around the MPP to derive the usable panel model. So applying the product rules to P equal V times I and setting dP over dV equal to 0 at MPP, we obtain the slope of IV curve. So alpha 3 was 0.31 and y-intercept was um, for for 14.84, and this gives us the linearized equation like that. So submitting this into the stated space average boost converter model, we derive the plant transfer function, which is a second order system with a negative neurometer. So this negative sign reflects the physical relationship where increasing the duty decreases the PV input voltage, which is constant with the boost converter behave with the output is fixed at the battery voltage. So for controller structure, we choose PI controller to achieve a zero steady state error, and this ensures the type 1 system, meaning a pole at the origin in the open loop transfer function. So for bandwidth design, we first confirm the LC resonance frequency was um, 45.3 radian per second. And this value is independent of RL within a given range of 0.03 to 0.1 ohms. So we just choose the 0.03 ohms for reduce the loss. And lower bound of bandwidth comes with the setting time condition with zeta was 0.9 corresponding to phase margin was 90 degrees. We required like that. So, but the upper bound is set to omega, upper bound is set to resonance frequency divided by 3, which is 15.1 radian per second to avoid exciting the plant resonance. So the given design of range was like that from 4.444 radian per second to 15.1 radian per second. So from this phase margin, we selected phase margin of 19 degrees, while the result in a slower transition response is it provides a sufficient stability margin against the plant resonance frequency. So we based on these constraints, we choose omega bandwidth was 6 radian per second and phase margin was 90 degrees. So next step is simulation result. Running simulation across all 6 measurement days using the BAS MPPT algorithm with our PI voltage controller. The average power tracking loss was 11.87%. And as seen in the plot, the tracked power showed in red, following the maximum available power in green, reasonable well during the steady state operation. But however, the noticeable gap are visible during the morning ramp up phase, and especially on day with the higher irradiance variability, such as January 30 30th, and February 5th. So these gaps indicates the voltage controller is not tracking the reference voltage fast enough, causing MPPT algorithm to operate in inaccurate power measurement. So average losses was 11% which is higher than expected. So after analysis, we identified the root causes because the CISO2 robustus CISO2 auto tuner when configured to phase margin was 90 degrees and um, bandwidth for 6 radian per second automatically places the PI0 at Ki equals 81.37 and more than 13 times for design bandwidth. And at the crossover frequency of 6 radian per second, the zero provides only 4.2 degrees of phase boost, effectively neutralizing the integral action. So as a result, the controller behaved almost like a pure integrator with a very slow voltage tracking response. So the recommended correction is to manually place the PI 0 at Ki um, Ki equals 1.5 to 2.0 radian per second. So at this position, the phase boosts at the crossover frequency increases from 44.2 degrees to approximately 71.6 degrees, enabling the PI control to function as intended. So with this section, we expected a significant reduction in tracking losses and improve MPPT performance under varying error condition. So in the conclusion, we successfully designed the simulated boost converter based on MPPT system using BAS algorithm with PI controller, voltage controller. But the hardware parameter was designed under STC worst case condition, and the control bandwidth was selected based on both MPPT updates rate and LC resonance frequency. And while the current implementation result is approximately 12% tracking losses due to PI0 misplacement, we have identified the root causes and proposed a correction. And with the Ki set approximately 2 radian per second, we anticipate a substantially improved tracking performance. And thank you for attention.